He's worked on numerous projects in the field of non-destructive testing and forensic investigation of structures. Don is active in several professional organizations and is in a leadership position in both ASTM Committee C12 on mortars and grouts for unit masonry and ASTM Committee C15 on manufactured masonry units. Mr. Harvey is the author of several papers regarding the use of non-destructive testing, historic preservation, masonry testing, and other topics. He received his Bachelor of Science degree from the University of Texas in Austin in architectural engineering and a Master of Science degree in civil engineering. Mr. Harvey is a registered professional engineer in Colorado, Iowa, Louisiana, New York, and Texas. So, welcome, Mr. Harvey. Don.
Good morning. Thank you for coming. Happy to be here. I apologize that I have those two ugly letters behind my name in a room primarily full of architects. I know that makes me somewhat the enemy, but I can assure you that I actually did start off in design studio at University of Texas and quickly figured out that I couldn't draw and fell back to engineering. So I'm not the enemy, and I actually won't be spouting a bunch of formulas at you this morning, physics problems, etc. I'm going to keep it fairly architectural in nature, I hope. That's the intent. Just a quick little tidbit about who I am, who Atkinson-Noland is, my firm. We're masonry specialists, basically, historic and modern. We look at some fun things around the world every once in a while, like some of these projects. And we look at plenty of modern construction as well, do some non-destructive testing, that sort of thing. But basically, we're the people who get called out when there's problems with masonry. So my objective this morning is to try to prevent some of those problems in your projects. That's the primary goal. Here's the AIA language. This you will be receiving continuing education credits for this. And here are our mandatory AIA Learning Objectives. I won't read them through word for word, but the basic idea is we're going to try to understand what masonry does better, what water does as it relates to masonry a little bit better, and then we're going to talk, because I'm an engineer, I have to get a little bit of engineering properties in, talk a little bit about some significant changes to masonry strength that have just happened in the codes, so that even if your engineer is not informed, at least you will be informed about some significant changes in that regard. The way we'll organize it, however, is into these four basic topics. What masonry does, what masons want. One of the things we do at our firm is we get a lot of calls from angry masons. You may get those calls too, but they may be a little bit less frank with you than they are with us, because they can use all the four-letter words they want when they're talking to us. We'll talk about what water does, and we'll talk about why your block just got stronger. So there was a miraculous transformation here in the past year or two. So what masonry does, it doesn't just sit there. So masonry, like just about everything that we build with, work with, does things even after we install it. Even though masonry is very stable, very solid, inert, etc., it still does move, shift, etc., and we need to understand that in order to better design with it. So this is going to be a little bit shocking for the masonry crowd in here. We have a big slide that says brick sucks. Fortunately, National Concrete Masonry Association was one sponsoring me here, so I can get away with this slide, but they're really not going to like the next slide. But brick sucks moisture out of the environment and expands over time. So the smallest a clay brick masonry unit will ever be is right when it comes out of the kiln. It is in a condition that we call bone dry. 0.00000% moisture, no moisture whatsoever. Over the life of brick, it gradually, permanently gains some moisture content and has what we call irreversible moisture expansion. So most of you already know this, but brick expands over time. That's why. It's irreversible moisture expansion. This is an important thing though. The brick sucks is just to help you remember it. This is the one that they won't like as much. Block stinks. No, actually block shrinks. Just a little typo there. But again, just a little memory aid to help you remember. Block sucks in, or excuse me, brick sucks in moisture and expands. Block shrinks over time. Those are opposite behaviors. One is volumetrically increasing, one is volumetrically decreasing. And that can create some challenges when you're designing and working with masonry. So we're going to talk a little bit about that. So if the material expands, brick expands over time. Therefore, when we put joints in brick, we call those joints expansion joints. Not everyone on every drawing that you see is going to call a joint in brick an expansion joint. The reason why I emphasize the terminology is because the terminology is related to the function. An expansion joint needs to be able to accommodate expansion. Therefore, it needs to be compressible through the thickness and clear of mortar droppings. In fact, we usually recommend that you intentionally fill expansion joints with compressible material through the thickness in order to prevent mortar from getting into that joint, clogging it up, and making the joint non-functional. So expansion joints need to accommodate expansion. On the other hand, control joints control where the cracking happens. Just like all concrete cracks, all concrete masonry cracks, we just want it to crack in the control joint. That's where we want the shrinkage to concentrate. That means not only do we need to have a joint present for it to crack at, we also need to do things like stop the bed joint reinforcing at the control joint to force it to crack at the joint. So those sorts of details become important. Another important little note here is that other masonry moves too. These are the two big categories that we usually design with and think about. But stone masonry, for example, if you have a 100-foot long run of nice stable sandstone, limestone, even granite, it still undergoes some volumetric changes due to temperature or moisture, etc. We worked on a bridge project that had some unfortunate cracking because there were no joints at all to accommodate movement. So what happens if we put a material that volumetrically expands in combination with a material that volumetrically shrinks? We don't stop either of those behaviors from happening. It's a very common configuration to see, but it creates some interesting results. So here we have primarily clay brick masonry with some concrete block accent bands. This is a joint. I hesitate to call it either an expansion or control joint because it's partially an expansion joint and partially a control joint. And it's actually behaving that way because the brick expansion is closing the joint there and the block shrinkage is opening the joint there. You can see the joint's significantly wider in the block area than it is in the brick area. The other thing you'll notice if your eyes are good is that there are cracks along the interface between the brick and the block. There will be cracks between every interface between brick and block in the entire building because they're going in opposite directions. So we'll talk about what some of the implications of this are. This is not just hypothetical, by the way. I went outside of my hotel room last night to get dinner, saw some brick with precast accent bands, and here's a crack where this brick is expanding and pushing the precast out. So this happens right here, almost in our own backyard. It's a real behavior. So how can this be avoided in design practice? If we don't want these sorts of cracks and delaminations, there are plenty of block products that give the same aesthetic or very similar aesthetic to brick, and vice versa. If you can try to maintain one material at least in a panel, it will significantly help to reduce this kind of behavior. This expansion, this volumetric expansion of brick and similarly shrinkage with block doesn't just happen horizontally. It is volumetric, so it happens in all three dimensions. Usually the thickness dimension we don't have to worry about too much because it's a fairly narrow dimension. But we do have to worry about it vertically. This is a hotel building in Denver where a lipped brick was used to try to minimize the joint beneath a shelf angle, and it minimized it so effectively that it didn't exist at all. There was just a fillet joint between the top of the brick and the bottom of the flashing above and the brick above. So the horizontal joint at the shelf angle, the width was effectively 0. This had an interesting manifestation in the brick behavior in the areas especially where it was exposed to direct sunlight and you had the biggest thermal cycles. The flashing at the shelf angle actually walked out of the wall, which is a really strange behavior. A lot of times you'll see spalling or cracking or other things like that. In this case, the setup just happened to be such that there was a little bit of a ratcheting action that gradually pushed that flashing out of the wall. So it was interesting that the wall started to spit out its flashing after a couple of years. Kind of an interesting project. So what about if we combine brick and block, not in the same plane, but supporting one another rigidly? So here's a tower structure with a block backup that was doing this. This is looking at the interior, some cracking in the concrete block. You can see these cracks were starting to get pretty wide. And we had a concrete block backup with these rigid truss type ties to the brick veneer. Not any kind of really flexibility for that tie to move vertically. So effectively what has happened, what has created these cracks is that brick has expanded and pulled apart the block backup as the block backup has shrunk because there was no allowance for vertical movement between the two. So you actually, in reality, your structural backup of block here is now effectively the veneer, and your brick is the load-bearing element because it has expanded and taken all of the load on itself, not the behavior you want. Pretty easy to avoid this. Even just had they used traditional ladder type ties, there's more flexibility in those, and it probably would have allowed the brick to move independent of the block, and certainly an iron pintle type tie system would have been effective in preventing that. What masons want, parenthetically from designers at least. We're not going to get too far into the brains of masons and their desires. That's a dangerous place to go. But we will talk about what they want from you, and that includes things like adequate detail, which I know is a challenge on a number of fronts. Modular construction, which needs a reminder every now and then, and constructible drawings. And the things that affect constructibility may not be the things that first come to our minds as non-masons in terms of constructibility. So adequate detail. I understand the normal fee structure that architects are faced with and the challenges associated with providing details for masons or for any other aspect of the building for that matter. But one of the big challenges with masonry and with other flashing and waterproofing details especially is that the typical detail often doesn't cover the situation that is most critical for leakage. Things like laps, corners, interfaces with different materials, etc. And if a detail isn't provided, masons are creative people, they can come up with something. The problem is what they come up with may not be exactly what you would like. So adequate detail is important. Similar to that, adequate detail on the drawings is important. I don't know how often you've followed masons around, but I've yet to see a mason carrying a spec book around on a project site.
Hey.
Some masons may be offended by that statement. They know where it is on the project site usually. But the more detail that you can get on the drawings, the better. The more likely it is to be executed in the way that you want it to be executed. Dimensions. Dimensions are important not just in terms of understanding where basic elements are in the drawings, but remember that sometimes it's important to dimension things through the thickness of the wall. Those are the dimensions that are neglected most often in masonry drawings, are things like how wide is the airspace or the cavity. Sometimes there's just a no 1-inch minimum cavity, and if you start adding up the dimensions of the exterior insulation and the brick itself and the waterproofing and the flashing, all of a sudden you're right at 1 inch or even less than 1 inch, and that dimension becomes really important. So dimension the drawings, especially in section view, that can be really important. Make note of special colors and textures and finishes. We're going to talk a little bit more about this on a separate slide, give it kind of an example. But those elements are really important to masons in terms of pricing projects, ordering materials, etc. And flashing. Flashing is kind of we could do a whole hour-long presentation just on flashing and masonry. But certainly make sure that your drawings, not just your specs, but your drawings indicate what type of flashing. There's lots of flashing materials out there now. In addition to self-adhered, we have copper, of course, and coated copper. There's stainless steel flashings that are becoming more popular now. There's various combinations and systems. So make sure you let the mason know what type of flashing. Where does it stop? Again, this is a through-the-wall thickness dimension. Where is the edge of the flashing? Does it have a drip edge? Is it held back? If it's held back, how far is it held back? That's important. How is it attached? Is there a termination bar? How is the termination bar treated? And laps, corners, and end dams. Again, those things that happen to the flashing away from the typical section often are the problem areas that come up later. There are plenty of wonderful resources for details out there. I encourage you to take advantage of them. There's 3D system drawings at websites like masonrysystems.org and IMI. Wonderful resources that oftentimes you can even download these details into CAD models and take advantage of someone else putting the labor into there. Modular construction. One of the things masons will say naughty things about architects behind their back is when architects don't provide modular design. Usually with modular design, you only really have to remember one number, or at least one number and its multiples, and that number is 8 inches, of course. So it's important, especially with openings and transitions, to make your construction modular. You don't want to have the mason have to, this is a little hard to see, but this is actually a lipped brick in order to accommodate the bearing of your lintel there above a window. And again, here we have kind of a half-height brick above the window opening. It's just as painful if there's a lot of awkward cuts on each side of the window, if your window openings are an awkward dimension. So with masonry, think through what your module is. Again, if you're using Norman brick or a different type of brick, then your module, at least horizontally, might change. But generally speaking, you've got 3 brick units vertically for 8 inches or 1 block vertically for 8 inches. That's the number to keep in mind. Oh, and a note there, see if I can go back. It doesn't like going back. 3-foot doors don't generally work well with concrete block. That dimension, 3 foot 36 inches, that's not a multiple of 8, and especially when you add trim around, you end up with kind of awkward slivers of concrete on either side. So just a note, if you can't avoid it, it's a good idea. Constructability, one other thing masons want, and apparently there is a mason in the room since he chided me earlier. Do you like working with normal weight concrete block? Lightweight concrete block weighs a lot less. I don't know when the last time you went around carrying some concrete block. We have a laboratory at our office, so we test concrete block every once in a while, and we carry it around. Lightweight concrete block is heavy enough. It's already kind of, you get your morning workout when you carry that around. Normal weight concrete block is darn heavy. And it's awkward to place, and because it's darn heavy and awkward to place, you will pay a premium for installation of normal weight, medium weight or normal weight concrete block. So if you are going to make the decision not to use lightweight block, you need to do so intentionally and understanding the consequences. By the way, lightweight block has some other advantages. Lightweight block is actually generally more fire resistant, has a higher fire rating than normal weight block. And water resistance. This was a controversial topic for many years in the Colorado market, whether or not lightweight block tends to be more absorptive, less resistant to water penetration, etc., especially in single wide block applications. And there were a number of studies that were done in that regard, and the answer to that is basically it depends a lot on what type of lightweight aggregate is used. Some lightweight aggregates, such as expanded shale, which is the primary lightweight aggregate in the Denver market, is actually very moisture resistant, whereas other lightweight aggregate that is inherently more porous is somewhat more absorptive and susceptible to moisture penetration. So if your rationale for not wanting to use lightweight block is moisture penetration, make sure that you understand whether or not your lightweight alternative is actually more absorptive and susceptible to moisture penetration before you rule it out. All right, so I told you we would talk a little bit more about special units, colors, etc. And we're going to do a little pricing exercise here to demonstrate why this is important to masons and why you might see change orders related to adding a little color band that you think shouldn't be that significant, etc. So special shapes cost time and money. Sometimes the time is the more important thing than the money, because special shapes require the manufacturer to usually set up a special mold, and there's some lead time before it can arrive on the site, etc. So here we're going to say that we're putting just a little special color band into our concrete block assembly. It's of course has some special pieces at the corners because we can't have an unfinished corner there. So the mason goes to a supplier, and the supplier says, well, you're going to order less than 2,000 of those units. In fact, of the corner pieces, you're really going to only order 4 or a dozen or so on and so forth. But since this is a special shape, we're going to charge you $700 just to set up the form. So for these corner pieces, we're going to have a setup charge of $700 just to start off with. Since those corner pieces are going to have some color, they're going to have some texture, etc., they're going to be maybe a couple bucks, $3 per unit. Not that expensive, right? But the supplier might say, depending on their policies, well, we have a 200 unit minimum. Well, I only need 4 corner units. Well, we have a 200 unit minimum. So at $260 a piece, that 200 block minimum puts them in at $500 for the units, $700 for the setup charge. So we end up with over $1,000 of material costs. This isn't labor costs, but material costs, basically just for 4 blocks. So, or however many corners you have. So you can end up with a significant charge for a relatively minor thing, and again, sometimes a significant delay if these are special units. So the earlier you can get this information to the mason, the better. The other thing to keep in mind based on some of this information is sometimes it's not that much more expensive to have 2 or 3 color bands than it is to have 1, because you're already going to be ordering kind of a minimum number of block anyway. So just something to keep in mind when you're putting your drawings together. Another thing that's beneficial to masons, but also beneficial to the entire design team and entire project team, are mock-ups. And I understand mock-ups can be expensive, they can be cumbersome sometimes, but they're a great idea. They're in the MSJC, now TMS 602 spec, and there's a reason why they're in there and they're so beneficial. They can serve as the standard throughout the project. Please, if you do a mock-up, don't destroy it until all the signatures are on all the papers, all the checks are signed, everything's out the door, because these have really served in numerous cases to help resolve disputes because they serve as the standard for standard of care for the work. Sometimes you can even do a mock-up if you're concerned about water testing of windows, for example. You can actually do a mock-up and go ahead and test performance of your mock-up before the project even gets started. And it helps identify potential areas of concern. So don't pull them out of the project. All right, this is another controversial slide that masons will cheer and architects may, you may get a little upset at me for saying this, but there is actually a standard for how we evaluate the aesthetics of masonry. Both in the brick and block ASTM standards, the reference for evaluating aesthetics refers to diffused light. You're to evaluate masonry in diffused light. What does diffused light mean? It basically means that we don't have sun raking, or sometimes you'll hear clocking across the face that's casting shadows. This side of the wall is in diffused light, this side of the wall is in raking light. We have a lot of projects in Denver especially. We have some pretty harsh sun angles sometimes where the project's going great, everything looks wonderful, architect is happy, they get to the south elevation of the building and all of a sudden there's shadows all over their masonry and everyone's upset and the owner wants it all ripped down and put back in, and it's a big mess. Those shadows are caused by non-diffuse light. They're caused by harsh sun angles. And you are really not permitted in the ASTM standards to evaluate masonry based on its appearance in that raking light. Now, does that mean you may not be happy with how it looks in raking light? Absolutely, but it is not the standard for evaluation of masonry. So be aware that that is something that's going on. And from 20 feet away also, by the way, that's a significant number, 20 or 25 depending on the standard. One thing that can help reduce those shadows, that just a little trick that you may or may not be aware of already. If you're using Norman brick especially very long brick or long and narrow brick, rather than using 1/2 bond, use a 3rd running bond. What this accomplishes is if these brick are tend to be a little bit fatter at the middle, any warpage, etc., you are not aligning the narrowest part of the brick above with the fattest part of the brick below and casting the widest shadow possible like you would with 1/2 running bond. With 3rd running bond, you're reducing that potential for shadow a little bit. So just a little trick. This is something I'm just throwing in kind of for your reference to make you sound a little bit more intelligent when you refer to masonry in general. The codes, as you may or may not have known for masonry, these are sort of the structural codes, but they deal with a lot of architectural issues as well, including things like mock-ups and installation standards and tolerances. Some people have, your engineers probably have referred to this as like an ACI 530 code. You may see that a lot of times. For many years, we technically referred to this as the MSJC, Masonry Standards Joint Committee Code, because it was a combination of TMS and ACI and ASCE. Recently, this standard has actually come under the control of the Masonry Society, TMS. So to correctly refer to the Masonry standard now, you should put in your specs TMS 402 for the code, TMS 602 for the specification. That is the correct name for the Masonry code now. So if you're referring to in your specifications, build in accordance with the masonry spec. That's TMS 602 now. 13 version is out there. What water does. We're going to talk about water and masonry and some of the challenges that can come up. What water does is it causes a lot of problems and a lot of lawsuits, as you may be aware of, hopefully not from personal experience. American Institute of Architects says that water intrusion accounts for about 70% of all construction-related litigation. Other things that water does, it goes down mostly. We'll talk a little bit about when it doesn't go down. It freezes, at least where I live and where you live. It can cause efflorescence, it can cause corrosion, and just flat out leakage into the building that people see and call their lawyers. Water also goes through masonry. I kind of made this fairly absolute. I didn't say it might go through masonry, it can go through masonry, it sometimes goes through masonry, it does go through masonry. How do I know water goes through masonry? Well, because, including well-built masonry, by the way. How do I know this? Because we do tests of water going through masonry. This is a test called the ASTM C1601. Some people call it the spray box test or the storm in a box test. Spray water on the masonry and you apply air pressure to simulate wind, and you see how much water gets through masonry. You actually measure it. And we're going to show a little video here. This may be a little bit hard to see with the light, but this is the back of a very well built, properly constructed clay brick masonry wall during that testing. Another thing to notice, by the way, is that those mortar joints look pretty on the front side. They're not quite as pretty on the back side. But that's kind of the reality of masonry construction. I think we get a little bit closer up here so you can kind of see the water dripping down. There's some water drips. So water gets through masonry. It really happens. Most people don't rip off their walls to actually test it and look at it, but occasionally we do, so I thought I would share that information. So if water gets through masonry, we need to accommodate that water getting through masonry and do something about it. What can we do about it? Well, we can select materials appropriately, we can detail appropriately, we can provide appropriate weeps and vents, we can detail single wide very carefully and very appropriately, because there we don't even have a second line of defense. We can look very carefully at our upward facing elements, because those are particularly prone to moisture infiltration. And again, there's a lot of resources available to help us with all of this. I'm going to talk first about caps and upward facing elements, primarily because these are some of the elements that are most prone to moisture infiltration. These are the first things that we tend to look at when we go to a site because there's a moisture infiltration complaint. Obviously, upward facing elements are more exposed to moisture. They collect rain and snow, and they're just more susceptible, more prone to moisture infiltration. What can we do to help minimize that? First thing seems very obvious, but we need to have some slope on those elements. Truly horizontal elements with no slope whatsoever are going to be very prone to moisture infiltration. So we need to slope it to drain, preferably slope it to drain away from the rest of the building, if you're at a sill, for example. We need to put flashing underneath these elements, generally speaking. Drip edges are a really good idea. It's kind of hard to see in this detail, but there's a little groove underneath each edge of this cap. This is one of those cases when water doesn't always go down. So water actually really likes to wrap around this sort of edge and migrate in. So the more that we can do to try to keep that water off of the surface of the masonry below, the better. So those drip edges are a great idea. And sealant in joints between mortar, sealant in joints in lieu of mortar is also something that can really be beneficial in terms of minimizing moisture infiltration, especially at caps, things of that nature. You can kind of see this, this cap element, there's one joint And right beneath that joint, there's a little sweat ring. There's a little efflorescence band, because that's where all of the moisture penetration into the masonry below happens, is at that mortared and, by the way, flat cap condition. And we've got a little sweat ring there. Again, you can kind of tell where the joints are in the cap by where all the nice long water stains are in the masonry below. The joints are the most susceptible part. If you make those sealant instead of mortar, you're going to go a long way to prevent this kind of behavior. Is this horrible? Is this destroying the wall? Probably not, but it's making the masonry below. You can see, obviously, this is in Denver, so we're a severe freeze-thaw environment. The more you saturate that masonry, the shorter the lifespan will be ultimately. Sealant instead of mortar can be a really good idea. Don't forget the flashing beneath. Upward facing elements, so there's numerous things that could be significantly improved about this style of cap. One thing is it's built out of brick units. We just said that the most susceptible portion of a cap to moisture infiltration is at the mortar joints. Well, how many mortar joints do you have in this cap compared to a precast cap or some other stone cap, anything that's a larger unit? You have a huge, enormous number of joints that are all going to be more susceptible to moisture. It's also dead flat on the top surface, and there's virtually no overhang, much less a dredge. So this is kind of a worst case scenario, and by the spalling you can see it's behaving like it's designed in the worst case scenario. It's getting saturated and it's not doing well. I guess there was kind of a half-hearted effort to remediate this condition, but again, we're using brick units with lots of joints, upward facing mortar joints, etc. Not a good slope. We can do better. Again, this is from BIA Technical Note 7. They have a lot of great guidance if you want some specific numbers, things like 15-degree minimum slope. If someone comes to you and says, well, why 15 degrees? Well, BIA Tech Note 7 says 15 degrees, so that's industry standard. Build it that way. Some good resources. This shows, by the way, brick in this particular detail, but in the text of the standard it says it's recommended that you use precast or larger elements to minimize those number of mortar joints within your construction. So here's a dead level sill with some snow collecting on it appropriately, as it does. These are some special units which are nice, or perhaps cut units to help accomplish that slope. Single wide walls. So single wide walls have some unique challenges when it comes to moisture management, because we no longer have a cavity drainage system to rely on to mitigate our moisture. So what can we do to minimize moisture infiltration at single wide walls? By the way, some of this is applicable to single wide clay brick as well as single wide concrete block masonry. The first one is not. But one thing we can do is incorporate integral water repellent. Integral water repellent, that topic is another potential 1-hour-long lecture in and of itself, because it gets into various types of chemistry and molecular sizes and all kinds of fun stuff. But from the designer standpoint, the things you need to know are if you use an integral water repellent in your block, you need to use a compatible integral water repellent in your mortar. And you need to ensure that that compatible integral water repellent in your mortar actually gets into your mortar, which is becoming a little bit easier now that we have some pre-blended mortars that incorporate integral water repellent into them at the plant. A lot of integral water repellents in mortars are still intended to be added at the mixer. If that's the case, then my recommendation to you is to do a little bit of extra due diligence to make sure, hey, why don't I see the receipts for the integral water repellent that you're putting in the mortar? Show me the guy who's responsible for putting the integral water repellent in the mortar. Those little extra steps could go a long way to making sure that that integral water repellent gets into the mortar. Why is that so important? Because actually, if you don't have a compatible integral water repellent in your mortar, you will tend to get a little bit of a repellent effect between the mortar and the block itself if the block does have that repellent in it. And you'll actually make some kind of fine delaminations within the joints and actually hurt your waterproofing performance if that integral water repellent is present. So that's critical, and it's worth checking up a little bit on as a designer to make sure it actually happens. And penetrating water repellent. Most integral water repellent manufacturers will say, we recommend that you also apply a penetrating water repellent at the surface in addition to the integral water repellent. That penetrating water repellent helps with wind-driven rain, more pressurized rain. It has better resistance for pressurized rain events, and it usually supplements the behavior of the integral water repellent. So if you use one, it's actually recommended that you use both. Type N mortar. I'm speaking to structural engineers this afternoon. This is one of the things that I will continue to fight with structural engineers about is using Type S mortar all the time. Type S mortar, fundamentally, for those of you who don't know about mortar chemistry, fundamentally the difference between Type S mortar and Type N mortar is Type S mortar has more Portland cement content. Since it has more cement content, that cement does a couple of things. One thing that cement does is it hydrates, it gets hard, and as it hydrates and gets hard, it shrinks. Shrinkage in your mortar can cause debonding and cracking and opening up of joints, which can then let moisture through. Type N mortar is less susceptible to that sort of behavior and generally performs better in terms of water performance, moisture resistance performance. Type N generally performs better than Type S. Type N is also almost never needed from a structural standpoint. If your structural engineer tells you, well, I need Type S because my wall isn't strong enough if I don't have Type S mortar, well, I shouldn't give you permission to say anything naughty to structural engineers, but tell them, why don't you look at that again? I don't know that you're completely accurate on that. You can recheck that. And at the end of this presentation, I will give you a tool to tell your structural engineer that actually you can look at this new table and your Type N assembly is actually stronger than the Type S assembly that you designed for using your old code. So I'll give you a little secret to help you get Type N into your building. Flashing in single wide walls is extremely important because you do need to try to get that water out of the wall as quickly as possible. One of the things, I won't go through everything, one of the things that comes up often in single wide walls is this bond beam issue. One of the reasons why this comes up is because in a lot of single wide walls there are bond beams that are installed strictly for the attachment of shoring. It's actually not something the structural engineer put into the drawings. They needed a bond beam at this location to attach their shoring, so the contractor just put it in. Of course, because they just put it in, it didn't even exist in the drawings. They don't put in any sort of flashing or weeps at that location. So it's best to have in your drawings flashing, weep type of details for bond beams and designate that those should be used even at bond beams not shown in the drawings, such as shoring bond beams, etc. A brick ledge, if you will, what we conventionally call a brick ledge, a recess in the slab at the base of single wide walls. This one detail can save a lot of heartache on single wide wall construction. It is going to cost a little bit more to get a little bit of a recess at the base of the wall, but just having this little recess that tends to push moisture out instead of allowing it equal access interior and exterior makes a big difference in moisture infiltration in single wide walls. So highly recommend that you recess the base of single wide walls on a brick ledge or a recessed ledge. Double buttering of head joints, again, I might upset a mason here. One of the challenges that we've had with single wide walls in recent years, especially Type S mortars and especially in hot and dry conditions, is plastic shrinkage of the mortar itself. one way, and that plastic shrinkage causing some cracks or debonding between the units in the mortar. One way to minimize that is to double butter head joints. Double buttering means you put mortar on the unit that's in the wall, and then you put mortar that's on the unit that's in your hand, and then you press them together. Typically, mason's laying block would put mortar on the block. I gotta think about this. Mortar at the block on the wall and push it in, right? I'm looking at my masons. All right, anyway, usually we would do it just one side. I don't lay block enough to do this. So anyway, normally you would just butter one side and push it in. Buttering both sides helps reduce that, that shrinkage cracking potential. All right, weeps and vents. This is one of my pet peeve issues. I should have apologized in advance for all the offensive things that I say. But this may be something that offends you. If so, I apologize, but I still stand by it. Does a rope weep? Is a rope a weep? I have a bad joke that it only weeps when it's sad. But ropes fundamentally do not behave in the manner that we want a weep or a vent to behave in masonry. Yes, they can wick moisture. They can wick moisture both into the wall and out of the wall. Moisture that's on the surface can wick right back into the cavity. Moisture that's in the cavity can sometimes wick back out, but it requires the environment on the outside to be more conducive to the moisture than on the inside in order for that to happen. What I like to say is that one of Einstein's first papers was on how wicking works. And I'm no Einstein, so I would rather stick with something that I can understand how the water gets from one side to the other rather than a rope, and keep it simple. So here's a question for you. What product does BIA recommend for weeps and vents and masonry? Anyone want to volunteer to be my sucker? I guess not. It's a trick question. So the BIA actually recommends for weeps open head joints. That is their recommendation. Why open head joints? Because you know that moisture can get through an open head joint. There's no question about whether it's going to wick in the proper direction. Also, air can get through and ventilate very well. However, I understand that in the real world we have things like yellow jackets and small rodents and other things that like to get through open joints. So if you need to use some sort of product to try to reduce pest infiltration, etc., there are great products out there. Just try to get products that come as close as possible, as close an approximation as possible to an open head joint. That's really the behavior that you want. What about weeps and vents at the top of walls, at the top of wall cavities? What is the purpose? Is this a good idea, bad idea, etc.? Fundamentally, it's a good idea. And the reason it's a good idea is because it allows air to flow more readily behind the brick, throughout the brick cavity. That airflow will tend to dry out the veneer more quickly and reduce the potential for efflorescence, etc. Now, putting a few vents and a few head joints at the top of a cavity does not make that veneer a rain screen. Technically, rain screens, you have to partition off particular areas and you have to have a lot of ventilation. You can get big enough vents in masonry to kind of make it function as a rain screen, but you're talking about square feet of vent area, not square inches. So it's not a rain screen, but it does help. One thing to note is that if you do want to put vents in cavity wall construction and veneer construction, make sure they're down at least one course, because you don't want the top course of your masonry to be essentially a weak course, because you're missing all of these head joins that can cause some cracking, etc. So make sure that those come down at least one course. But they're a good idea basically for air circulation. Flashing. Again, we alluded to this earlier. There's a lot of options in flashing these days for masonry, a lot of different products you can consider. One thing that architects hate to hear, but is true, is that drip edges on flashing significantly improve their performance. If you can live with the aesthetics of having a drip edge on your masonry flashing, it's definitely a good idea. Drip edges both do a couple of things. One thing they do is they make sure that you get this flashing all the way out to the edge, which with a self-adhered flashing, sometimes you have to recess it a little bit so that it doesn't melt and bleed onto this masonry surface. If you recess it a little too much, then all of a sudden you're back at the brick cores. I think we have a slide of that later, and you're not actually getting the moisture to the surface at all. So they get the moisture to the surface, and then once it gets to the surface, they actually get it off of the surface of the masonry below, prevents it from just continuing to wrap around and go right back into the masonry. So they're a great idea. I know that's not a popular thought in this room, but they are really worthwhile. End dams. End dams can be somewhat of a controversial topic as well. Most masons now are a lot more used to the idea and the installation of end dams than they were 5 or 10 years ago. So if you detail and you specify, again, really detail in the drawings is the way to get these done. End dams, you have a pretty good chance that your masons will actually build it that way now. And they're a good idea. End dams or lack of end dams generally doesn't lead to moisture infiltration to the interior, but they are a beneficial way of making sure that the moisture above the flashing does actually get out where you intend for it to get out. So end dams are a good idea. Make sure that your flashing and your weeps are coordinated. If your weep is a course above your flashing, that means that this bottom course of masonry is going to remain saturated a lot of the time. I want to try to prevent that. A little bit about grouting in lieu of flashing, if you will. Grouting masonry in an effort to make it waterproof. Most grouting, especially conventional grouting, does not make masonry waterproof. In this detail we have flashing up here and we have their bottom courses grouted solid. Well, what does grouted solid mean in masonry? Grouted solid means that the cells in the block are grouted solid, which is fine, that's great. Where did we say most moisture penetration in caps, for example, happens? If you can remember back that far, at the joints, mortar joints. When you grout concrete block solid, what do you do at the mortar joints? Nothing. You still have a mortar joint at the front, and you have a mortar joint at the back, that's it. So grouting masonry solid does not make it waterproof. As long as you understand that and accommodate for that, that's fine. But this detail, for example, where we have waterproofing down here, but not up here, and we're anticipating that this grouted masonry can resist moisture because it's grouted. Try to remove that misconception from your head if it's in there. We're filling up these cells, we're not doing anything here. So, common detail recommended by BIA is to hold back bituminous flashing, self-adhered flashing, a ½ inch back from the face of the wall. Why is this? We already said because that bituminous flashing, when it gets warm enough, when it gets hot enough, melts and it can start leaking or bleeding out of the face of the masonry. So we need to hold it back for temperature reasons. But If we hold it back too far, especially nowadays, the cores in brick have actually continued to get closer and closer to the face of the brick. A lot of brick that's in the market today as veneer brick is technically no longer considered a solid unit. It's actually considered a hollow unit. Your specifications may reflect that now. Part of the primary reason for that has been to reduce the weight of the units, reduce gas consumption, transportation costs, etc. One of the side effects is that those cores in brick have continued to kind of gradually grow over time and get closer to the surface. Now this actually seems like it may even be closer than 3/4 of an inch from the face, but that is the minimum that you can have. But you're only giving a mason 1/4 of an inch of tolerance on how close he can get that flashing to the face. That flashing is generally cut using precision laser technology. No, just kidding. It's usually cut with a utility knife without a straight edge. So 1/4 of an inch ain't a heck of a lot for a guy with a utility knife without a straight edge to have in that plane. So again, this is one of the motivations for getting a drip edge on there if you can. Again, an end dam in particular situations becomes a really good idea, especially when you have interfaces between different materials happening. Certainly stopping the flashing short of the end of the lintel is a bad plan, but getting an end dam in there would be even better. Lapping seams. This is one of those things that we mentioned that's not usually in the typical details, but is typically in the lawsuit. Lapping seams is one of those things that can be done wrong pretty readily and is important. Not only should seams be lapped, but they should be properly sealed. A smear here and there, especially if you've got a little bit of cupping and bridging at the back, is difficult. Now, this back corner, we don't have a real big slide on this, but I should mention, this is actually an incredibly difficult thing to get watertight at a 90-degree angle. If we were doing this detail at a roof, what would we have at that inside 90-degree corner? You'd have some sort of triangular piece to allow the roofing to bridge across that corner without coming apart. We don't usually do that at brick flashing, at masonry flashing, but the same principle applies. In fact, a lot of times these are basically the same materials. You have sheet good materials that are trying to be tucked into a 90-degree corner that don't really want to be tucked into that corner. So putting a little kerf in there, a little triangular piece, really is a nice idea if you can accommodate it in your project. All right, last section. This is for you to take to your structural engineers. I'm going to be speaking to structural engineers later today, so hopefully a lot of your structural engineers will have already heard this from me today. But in case they do not, you can be smarter than your structural engineer in terms of structural capacity of masonry after this morning. Recently, the National Concrete Masonry Association, also NCMA, not the local NCMA, but the national NCMA, did a series of tests of concrete block assemblies, modern concrete block assemblies, to determine what the appropriate strengths. F prime sub m is similar to F prime sub c in concrete, which is just compressive strength, basically. What are appropriate compressive strengths for modern masonry materials? The last time that this type of study had been done was back in the 1980s, and it used materials all the way, and studies all the way from the 1950s to the 1980s. Our concrete block manufacturing processes have changed significantly since then. We have a lot more consistency in block manufacturing, and we were due for a refresh. NCMA did some testing up at their laboratory in Virginia near DC, and they came up with a new table. The new tables are a little bit confusing because, for one thing, this column, which is our compressive strength column, went from the right side of the table to the left side of the table, just to kind of make everything a little bit more confusing. Actually, this was more confusing than this, so they did actually put it on the correct side now. It makes a little bit more sense. But in order to summarize, this is a bunch of numbers. We'll look at kind of an example of what the difference is between the old table, old meaning as recently as 2011, and the new table, which is in the 2013 TMS 402 code, formerly known as MSJC code, sometimes known as ACI 530 code. Back in 2011, if we had, and I'm going to do well, I'll do the type S example because it's, the numbers are rounder. But if we had a type S mortar, which hopefully you don't, and you had a block that was 1900 PSI compressive strength, which was the minimum for the ASTM standard C90 for block. So a lot of engineers use this number or this number here. Type S mortar, 1900 PSI block. Your compressive strength of your assembly, which is what the engineers use for design, was 1500 PSI. So because the mortar is a little bit weaker than the block and you have some various effects, your total assembly strength was about 400 PSI lower than your block strength. In the new table, we have a new minimum block strength in C90. The new minimum block strength is now 2000 PSI instead of 1900 PSI. So the lowest value you should really ever have to use on this table is now 2000. As opposed to, I'm sorry, I'm circling the wrong thing. 2000 instead of 1900. So if you have 2000 PSI block, a type S mortar, now your assembly strength is in fact 2000. So your minimum compressive strength for a type S mortar assembly is essentially now 2000, and it was 1500. 1/3 increase in your strength. Can be very significant for your structural engineer. So here's a little bit of statistical data about how those were developed. I don't think you probably care about that, but if you run into structural problems on a masonry project, this is for concrete masonry units, by the way, this is not for clay brick. The change was just for concrete masonry units. If your structural engineer had some low breaks from the lab, runs into a problem with strength, etc., etc., the cheapest way to resolve that issue now is to tell the mason to buy your structural engineer a new code. Because in all likelihood, if he looks in the new table instead of the old table, his numbers will then work. And we've actually done that on a few projects. We've had some projects where a structural engineer has called us and said, I got low breaks on my project. What do I do? I'm in a panic. And I said, okay, what numbers did you get? I looked at it in the old table, it didn't work. I looked at it in the new table, it did work. I said, buy a new code, and your problem went away. And they did. So, so as an architect, usually you're not going to be dealing with structural properties, but on your next project where you have a panicked structural engineer, you can say, hey, have you looked at the new code? It might just work out after all. So that's all I have. Appreciate your time and your attention.